Good morning. I'm Hussain, former professor, Department of Chemistry, University of Dhaka. We are talking about X-ray crystallography and solid-state chemistry, and this is the 19th lecture on single crystal structure determination. Well, we were talking about how to collect single crystal data, and that is another lecture on it. Okay. We have been talking about Weisenberg camera and what are the use we can do with Weisenberg camera. First of all, we can have rotation and oscillation photographs. What do you do with rotation and oscillation photograph? In the right, you see this is a figure for rotation photography of single crystal. This figure immediately tells that the crystal has been aligned perfectly because this row, these are aligned properly and parallel to each other. So it says that the crystal has been aligned properly. When you get this photograph, what are the things we would get from the photograph? First of all, how the alignment has been done of the crystal. The second, we can measure the cell ages along the axis of rotation, and third, the preliminary symmetry information. That's what we can get. Well, every experimental data has some disadvantages. The disadvantage of rotation and oscillation photograph is that we get a two-dimensional reciprocal lattice plane, but it is condensed to one-dimensional layer line. That makes a very tedious job to index reflex. Many photographs are to be recorded to avoid possible overlap of spots. Therefore, it is desirable to get a record of a single lattice plane in mapping onto the entire sheet of film. Indexing becomes simplified greatly, and if it is straightforward, geometrical relation can be established between lattice and the photographic image. Okay, this method, as I say, was first proposed by Weisenberg in 1924. But the technique is rather simple. A singular line can be selected by slotting a screen and then take the whole single layer. You can see this is a single layer, and it is a upper layer photograph. This is single layer, and we can just collect this index single layer reciprocal lattice planes. Okay, and then we can see the Weisenberg photographs. What you do, entire all information about 3D structure determination. This photograph we record, and we can get all information. What are the information? I say improvement of crystal alignment, measuring of cell parameters, determining of space growth, determination of intensities of reciprocal lattice points, to collection of single crystal data for three-dimensional structure. One thing I have to specify here, that the theory and practices of photographic data collection is well discussed in many textbooks. I can suggest one or two textbooks, what I did in the beginning of the course lecture. This Weisenberg photograph data collection is very well discussed in a textbook. It's an X-ray structure determination, a practical guide. Author is Stout and Jensen, publisher William Sachs. Another one is very lucidly written, that is Solid State Chemistry and its application, author Anthony R. West, publisher William. Other than these two textbooks I mentioned, there are many textbooks, and I use here teaching materials to learn about these Weisenberg photographs and structure determination of single crystals. Well, it was said that in 1924, we are talking about the single crystal data collection by Weisenbach photograph. Then in 1940, we have another camera, which is precision camera. And that's what is shown here, a commercial equipment with precision camera. And if we remember that on the reciprocal lattice onto one sheet, film sheet, but this is unlike Weisenbach camera. This precision camera has got undistorted record of weight, undistorted. This is undistorted, whereas Weisenbach camera distorted. So that makes that this photographs or the data collection by this precision photograph makes life a little bit easier to index, measure, and search for symmetry. Okay, and then you can see this is a perfectly aligned crystal precision photograph of 0HKL net. However, misaligned crystals shows like this. So you can see clear distinction between a crystal which is aligned properly and a crystal which is misaligned. Next is that, well, we have been talking about how to collect data, and we were talking about only film methods. But there is advancing, and we see that another method, which is quantum counters method, and that is started in around 1960, diffractometer. People are now using in all solid state laboratories, almost all solid state laboratories, they are using diffractometer to collect single crystal data for 3D structure determination. Here is a schematic diagram of a post-circle single crystal diffractometer, single crystal diffractometer. Here is an incident X-ray beam, here is a crystal, and then the undifracted state moves there, and we have beam trap here, and then we have some circuit, chi circuit, phi circuit, theta, omega circuit, etc. And there is the diffracted beam. Here we get undifracted beam, which goes straight to the beam trap, and there diffracted beam, which we are in the counter. Well, this is what I showed, a schematic diagram for circle diffractometer, which are available nowadays in the market, and very many different types of four circles. Here is one such a commercial diffractometer, four circle diffractometer. I would say those who are very interested to go through single crystal structure determination and using diffractometer. Every diffractometer has got its special sum point, so we have to think about it and work on it. Well, a diffractometer, whatever commercial equipment, has 4 arcs, which we show here. There are to adjust the orientation of crystal and counter so that to bring desired plane, the desired plane to a reflected position, and then collect intensity of the reflections. These arcs are because pi, chi, this is a chi, this is a chi arc, this one is a chi arc, pi arc, and then these are 2 base arc, omega arc, and 2 theta arc. Okay, so these are the main point of diffractometer, and that's what is when you do instrumentation, it looks like this. Anyway, we know now there are 4 dots by which we will first orient the crystal and then bring to it in a desired plane and then collect intensity, and that is what we call data collection. Well, as I said, there are 2 basic circles, omega and 2 theta. Omega and this circle is 2 theta, this circle is omega. You see. Okay, about the common axis, and you can adjust independently or they are together so that their movements are correlated. Okay, the orienter is mounted within omega circle and pinned so that it rotates with omega. Okay, the last time we have here is that this is that when we rotate this guy, this guy at the B at 0 degree, you see that omega, 2 theta, and phi are coaxial when chi is 0. When chi is 90 degree, we see that omega and 2 theta are coaxial. Okay, this is what we have to remember, and we can get a segment of a chi circle. I mean chi, a segment of chi or full circle. So we have phi, omega, and 2 theta are true circle, but chi can either be a full circle or a segment of. This is a segment. This. Okay, now we go to next slide. What are the things we have to remember now? That we have to have a goniometer head attached with the y-axis, and generally a eccentric head is used, and this head is adjusted from above rather than below. If we adjust it from above, then we have more space to adjust the orientation of crystals. That is the advantage of it. There is common center to parts. Okay, you see this goniometer head generally of 49 millimeter, but in practice the heads can be up to 63 millimeter of height. Main difficulties, one of the main principal difficulties, diffractometers, number of axes involved in the orientation processes and necessary for their precise intersection. We have to do that precise intersection. If not, we can properly aligned instrument. The properly aligned instrument is that it is not more than 0.0254 millimeter sphere. Okay, but this is not extreme. A very careful attention to be given to the by the manufacturer and user of diffractometer for orientation process. Well, we always validate an instrument when you work with it. So similarly here also a diffractometer to be properly set up and oriented properly before we do collect the crystal. That what have to be ensured properly. Otherwise, what happens? You will get wrong symmetry elements, wrong initial, etc., and thereby all data becomes wrong, and thereby your structure determination also wrong. We have now detected some of the single crystal data by diffractometer, and the paper printed already, published already, has mistakes with symmetry detection and also cell parameters, cell ages, and thereby the structure has to be determined again. Well, this up to all, then we have to have an X-ray tube and a detector. So main focal spot of the source of X-ray, the center of the orienter system, and the center of the detector aperture should lie in a plane accurately perpendicular to omega or 2 theta axis. Okay, we used to use Geiger-Müller counter or proportional counter to get the data, but nowadays, especially scintillation counters are used. This counter gives more efficient, and we get more relative intensity a little bit more better. And we also use molybdenum alpha radiation mainly for single crystal data, unless the molybdenum alpha radiation damage the crystal. If it is so, then we choose other radiation, but mainly molybdenum alpha radiation. Then we do have a regulated power supply, a scales of counting, a rate meter, and etc. And we have to, from the pulse, we have to look out for weaker and stronger reflection, and then adjust this scaling using the expected energy, characteristic energy that are used. Okay. The main elements of the X-ray diffractometers have been discussed, and to get further discussion or further readings, you can use textbook as well as manuals provided by the manufacturers. Here, these are schematic data, not the real data. These are schematic data to let us see what we can do by reciprocal lattice plane or reciprocal lattice point. One thing is we take a distorted sections using Weisenberg camera, if you remember, and this undistorted section, these are generally recorded by precision camera, or another diffraction technique, that is transmission electron microscopy and diffraction, which is widely used for unit cell and space scope determination also nowadays. And also the nowadays transmission electron microscopy shows that we can use three-dimensional structure of nanocrystal, which we could not use earlier by X-ray diffraction. So electron microscopy and and X-ray diffraction techniques are complementary to each other. So we have to find out systematic absences of reflection, and also that can play a great role to choose the lattice style as well as space symmetry elements, which tells us how to find out the space loop and so on. So here we are showing a schematic section of the reciprocal lattice, single single domain with relative intensity, indicating by a spot. Relative intensity means by a spot. You can see this is a very systematic spot, and that's what is the origin. Undiffracted ray passes through it, and this is the origin also. And then we can find out the symmetry element from here. And we can see that if we take this section, we have a mirror plane. There is the mirror plane. If we just paste this section, it shows a mirror plane. Also, that the vertical one shows a mirror plane too. We do remember this is a schematic diagram, and it is not a diagram recorded from instrument. Therefore, in the instrument diagram, you might see the variation of intensity, but here we are showing the intensity of a symmetrical intensity. So we index it. If it is 0, 0, 0, then this one is 1, 0, 0, because this is an A star unit cell axis, and this is a B star unit cell axis. If you remember, we were talking about reciprocal lattice axis A star and B star designated by this B star. So if we do so, then this is you see 1, 1, 0, 0 reflection, and this is 0, 1, 0 reflection, and this one is 1, 1, 0 reflection. There, in this way, we can find out also the unit cell of this particular schematic data set. Okay, next we go a section of schematic weighted reciprocal lattice with relative intensity indicated by spot size, as I said, as shown in figure 1A and B. The center A, I also talked about, it is the undiffracted beam rotation and segmentation, so the origin of the reciprocal lattice or real lattice. And we look for the possible symmetry and spot in centric distribution to identify the most appropriate reciprocal lattice access. That's what is said. And this what we explain here, how this A star, B star, that's what we have already done. And then you say that, then you see that the equal intensity spot. What are the equal intensity spot? If it is one, if we take this one and this one star, and then you see that this is 2 star, and this is 2 star, 1, 3 prime, 1 prime, 1, 2 prime, 1, 3 prime, and similarly 2 prime, 2 prime, 2, 3 prime. Consider the overall crystal symmetry is likely to be orthorhombic or higher. So from here, the symmetry elements we can find out, and this one says that is that there's a mirror plane here, and also a mirror plane here. So if we have 2 mirror planes, the symmetry seems to be an orthorhombic one or higher than. Okay, this much we will see. We'll talk about unit cell reciprocal lattice and what is systematic absences, which we call extinction, by which we can find out also the lattice type and other space symmetry elements, which we will talk in the next lecture. For this lecture, thank you very much. I again repeat that these are the work, or these are the points to be checked and tested, and also do some homework to get it in your grip to understand what it does mean by this data collection and unit cell or reciprocal unit cell, etc. We take another or 1 or 2 lecture maybe about single crystal data collection, and then go for data reduction, how we do data reduction, and finally for how we determine the 3-dimensional structure. Thank you very much for your attention.